Hello and welcome back to another episode of Effective JaRu, the series where we will read effective Java and see if we can port the items over to idiomatic Rust. Unfortunately, I've been reading far further than I have recorded, so yeah, that doesn't actually represent where we have been. Even though last time I actually put the cursor there, so just have to skip through that for a moment. Item 34. You want to see the item 33, we want to see the, Jesus Christ, the phaser, the phase stuff, which is a very nice example on how the programming language is different, how your design changes with the language, and I think Java really makes you use very elaborate, complicated designs with a lot of runtime stuff happening, even though, or runtime heap allocation happening, even though this works entirely without, possibly. So where are we? Item 39. We are very close now. 33. As you can see, I'm well prepared, but I have done this recording before, but for some reason my recorder didn't start recording it. I didn't realize that until it was too late. So emulate extensible enums with interfaces. It's 34. You want 33 after all. Let's try that again. Yes. No. Still not. Excuse me. Here we go. 33. Use EnumMap instead of ordinal indexing. So the idea is that some people use the ordinal ID of an enumeration constant, in order to put it as a key into a map. And this notion doesn't even exist in Rust. If you want it to be hashable, then, well, it needs to implement the hash function. And that's pretty much it. In Java, though, you have a special type, which is an EnumMap. It implements the map interface, and it's optimized to be used with enumeration variants, which is quite amazing. That's Java. You have lots of different specializations, which are just that. It's a specialization of a general interface. Whereas in Rust, you prefer aggregation in a way. So if you want to have a thread save or synced access to a vector, then you put it into a mutex, right? So you add functionality to something that didn't have that before. The great thing is that these concepts remain totally orthogonal. Basically, you implement the mutex, you implement anything else that is not synced, and if you put those together, you have a synced something. Whereas in Java, you happen to have concurrent hash maps and specialized versions of everything that are made for certain use cases. And let's say it's more complex, more maybe even complicated to know all that stuff. Especially when multithreading comes in, I think you have no fun with Java, but that's just my opinion just yet. Maybe it's super great and awesome with the right frameworks, right? That's always like it. Use the right framework. Whereas in Rust, this stuff is built into the language to the point where you are safe, that is. So what do we have here? We have a phase, and this phase enumeration just knows that there is a solid and liquid and gas phase, and there are transitions defined here, and each transition transitions from one phase to another phase, and the name itself is then the transition. So that's how that is ordered, but this is really just a data structure here, which is set up like this, and I don't know why this is made like that. I mean, look at that. I don't know, some auto formatter that went crazy there. It's probably nicer looking like this, but anyway, this is just a dumb data structure, and then in the static initializer, you build a private static final mapping here from a phase to a map of another phase, which is source, destination, and the transition that would correspond to these. This is nothing else but a cache, right? You could just implement this manually by searching the data structure yourself, but it's not done here. Instead, in the static initializer, he will basically iterate the values of the phases, then initialize the EnumMap, initialize this mapping M with a EnumMap that represents this one here, and then once again for each transition it puts in the values into the respective mappings. So get the get the EnumMap that you have just put previously, and then put a new item in there, which is the transition name and the destination phase and the transition that leads from source to destination. And that's really it. So the in the actual implementation here just allows us to, in the static way even, which is quite odd to me, allows to basically convert from source to destination. I think this one here, I think this mapping here is on the transition enum, so it's in the nested type. It's not on the phase. And maybe actually it makes no sense to kind of make this a instance method instead, just because the way this stuff is looked up is really from source to destination. I really doubt that this is a suitable way of doing it, because the transition itself, I have the feeling it can live, it doesn't have anything, it can live without knowing the phases. But here it's kind of mixed together. It kind of lends itself to do that, probably in Java, because you can do nesting, and in the scope of the task here, it might seem like a great idea. However, in Rust, that's not even possible. So in Rust, you kind of by default specify your enumerations separately. So right now they have nothing to do with each other, which is a good thing. Also, it's not possible to have enumeration constants here. So enumerations are real values, basically. Or enumeration variants are real values, they're not constants. So you use them kind of differently. And in my implementation here, or let's say in the Rust implementation that I made up, you have a instance method on the face enumeration that allows you to transition to something. So basically you can say solid transition to liquid, and it will possibly provide you with a respective transition. Possibly just because transitions from solid to solid are undefined, so none would be a valid return value. So just to make it a bit easier and less verbose at the beginning, or just local to the transition to method, the variants are imported here into the namespace so that we can just refer to them without having to repeat ourselves and name the entire namespace all the time. So we match on ourselves because we are a phase, right? And then say, okay, if we are solid, then we shall return some, and then we match on the other thing. And if we are solid mixed with, or solid to liquid, then we melt. Solid to gas, we are subliming or something. And solid to solid is undefined. So the cool thing is that the return value, or the return type of this match expression, is a transition. And two of these cases return the same type, so that's fine. One of them just returns the entire function, so isn't considered as part of the return value, right? Because this just returns early. This is why that actually works. Here we return early. We return the correct type, whereas here we will wrap the created transition into some in order to, again, make it the correct type. So we repeat this for all the options and all the possibilities we have. In this case, it's really simple to do because they're just a few, we just have a few phases here. So it's really easy and well-looking, well-defined what we are doing here. And it's also fast, it's all static basically, it's all compiled in. There's no dynamic lookup, no heap allocation going on at all. So if you run this program, as you can see here, he iterates through the phase values, makes sure he doesn't compare phases that are the same, because that would actually return null here, right? Null is a valid return value, which is always the case, whenever you get an object, or a reference basically, then you can always get null. It's a possible return value. You probably want to make sure you don't get null, or have to read the documentation whether null can be expected or not, or whether it will throw or not, and all this stuff. It's kind of makes makes it difficult to reason about your software and really know what it's doing. And also remember this, because you will always have to consult the documentation for this. And documentation is, sometimes non-existent, sometimes it's wrong, and the compiler can't help you with that at all. So if you run this, you see after 0.03 seconds that it can figure this out correctly. So if you run this version here, the Rust version, we get the same result. Yeah, we run we use cargo run, so basically the entire Rust C toolchain is working beforehand. So if you time this, then it's 0.003 seconds. So it's actually 100 times faster in execution, just because it doesn't have to deal with all the Java stuff. And it's just a debug binary after all, right? So this is not even the smallest, sleekest binary that there is, but 301 kilobytes. And you are done. So that's pretty neat. You get the same result. How does it look like? Here, yeah, that's the thing in Rust, right? We are not able to iterate enumerations. It's a question of whether this is ever needed. I have never needed this for my own use, because the way you use enumerations in Rust, you actually don't need it. When you need a particular variant of this one, you instantiate it explicitly. And Rust will check, or will assure that in match statements you are safe, so that you will have to be exhaustive in your branch with your branches. Make sure you handle every variant that there is, or have a default case. But here we are not protected of that, because here we explicitly put in solid, liquid, gas phases in order to be able to iterate them. Then the code looks pretty similar to the Java one, where we just print the line to the output here. Even though our actual call looks a bit different, it looks, Java wants to force object orientation onto you all the time, and is very restricted in that way, because, it's not always a good fit, not for everything at least. And for some reason, just because we are using Rust, we didn't do this nesting stuff. We put the transition handling into the phase, which is where I think it goes more natively. And then you can do, P1 transition to P2. And we unwrap this because we kind of know that this is a valid thing. But this code also shows that we do an unwrap here, so that can possibly panic, right? Whereas in Java, if this happens to return null on you, then you get a null pointer exception. Which is kind of the same thing, but it's less explicit. It's like, oh, there was a null pointer. Well, what happened? Whereas in Rust, it's clear that, hey, you're unwrapping something without checking, which expects it to be something, which is kind of different semantics. You are more proactive there, where in Java, you happen to just run into this, and the runtime tells you that something is wrong with what you tried. And it might even tell you later, because you can just obtain a null value and use it and store it and do stuff. So you basically happen to put the actual problem, or see the actual problem, or see the problem later in the program execution, which makes debugging harder. In Rust, if something is wrong, it will go wrong right away. That's the awesome thing, and you can't get around that. You can be sure that stuff goes wrong right away, which is awesome, because that shows you where the problem is right away. So that's item 33. I think that shall conclude this episode. Kind of a nice little example here, shows the differences. And I think generally in Rust you will actually come up with slimmer, nicer, more fitting architectures, just because of the design, or the freedom of the design that you have, which kind of forces or to keep things orthogonal, and keeps the model in your head easier. That's how I feel. So that shall be it for now. Thanks for watching, and have a great day.